she will tell us about the unified interorbital triplet superconductors and spin density wave in layered rootinates. Actually, this series is very nice because we start from Stephen Hayden's talk about Sr3Ru2O7. We end, this is the last lecture for the semester because school stops after this week. So she will talk about also Sr3Ru2O7. Hopefully she will completely enlighten us on the understanding of this material. Yeah, thank you, Hae Young. It's all yours.
Okay, thank you, Feng-Cheng. Thank you for the invitation. Yeah, I remember Stephen's talk in the very beginning, so it's glad to go back and try to link what we studied, try to give you some idea of what we have been doing for the last few years. So my title is, as written here, we try to understand the inter-orbital, well, actually a superconductivity in a single layer 2-on-4. To a field-induced spin density wave in the bilayer 3-7. Okay, so this is the reference of the few of work that we did. And you can see that 3 of them is very recent, but in fact, that this goes back to my former student, Christoph Putter, who worked on this identifying spin triplet pairing in spin-orbit coupled multi-band superconductors back in quite a while ago. And recently, Austin and Jonathan has joined us to give me more information and learn more about what was going on. Okay, so let's begin with the periodic table. I mean, we've seen this, 1,000 times. When we are talking about 3D, we are interested in the transition metal, which is this pink area. And in fact, the 3D material, we talk about this Hubbard models and so on. But if one is interested in the 4D and 5D, we know that there are significance of this spin-orbit coupling because they are heavy atoms. And they also appear to have the Hund's coupling that are important because unlike the high tissue cuprate, which is a single orbital, many of these compound comes as a multi-orbital. And there, Hund's coupling will become important and they play quite an important role. So recently, I was interested in the rutheniums here for the atomic number of 44, and 2 of the compounds that I work rather intensely are, in fact, it's the layered ruthenate with 2-on-4 single layers, and another one is the ruthenium trichloride. This is another very interesting object. They are very different though, because strontium ruthenium-O4 has the 44, so the occupation is that telling us that T4 is going to be, in this case, is a metal, and the bandwidth is much bigger than the spin-orbit coupling, which is about 100 MeV in this case. In this case, I'm going to talk about superconductivity, and that's where the spin-orbit coupling and Hund's are going to play an important role. On the other hand, for the ruthenium trichloride, is that where spin-orbit coupling is actually even bigger than the bandwidth with the honeycomb lattice. It comes with a T5, and this is a multi-insulator. And where again, spin-orbit coupling Hund's plays a very important role to generate this microscopic interaction called the G-type and gamma interactions. So today I'll talk about this strontium 2-on-4 as well as its sister compound, which is the 3-7. Okay, so ruthenate series is somewhat has an interesting history because it actually started with trying to find the high TC because this 2-on-4 has isostructure to a cuprate, strontium to copper oxide. And there are a series of this transition metal oxide which were motivated by looking into searching for a high TC appearing in non-cuprate, non-copper, without the copper. So, but then instead, it was actually a superconductor with a TC of 1.5 Kelvin. And N=1 is referring to single layer. And here's the structures which plays the important role later on. On the other hand, for the 3-7, again, it's a sister compound with N=2, meaning bilayer. And note that this angle theta, which is different from the single layer, this is 0, while this is 6.8. There is a staggered rotation of the octahedra, which again plays an important role. So I want to tell you that just pay attention on some of the details here, like a single layer with a superconductivity with 1.5 kelvins. And on the other hand, bilayer comes with two of those ruthenium oxide. And in the plane, if you look at AB in a plane, it has this octahedra rotation, meaning ruthenium here to oxygen, ruthenium are not straightforward 180 degree, but it's rotated. Okay, so that's the two difference between the layered ruthenate. And the puzzles has been like this superconductivity of 214 has been known since 1994. It's a very old, in some sense, it's kind of old subject, and there has been lots and lots of people have been working on this. And still the puzzle appears to be that what is the pairing mechanism in 214? And of course, associated with that is what is the pairing symmetry, which I will be able to talk about if I have some time. Otherwise, I'll just focus on the pairing mechanism. And that is not independent of the fact that we don't see the superconductivity in 327. So like, remember that I said that this was initiated by high TC, and in a high TC compound, whether you have a 214 or you have bilayers or you even have a chains, they all appear to have very robust superconductivity, while here it is very, very sensitive to any changes. And that's what somehow led to the people think that this might be a triplet as well. In addition to the fact that the 113 compound, which is a three-dimensional version of it, is a ferromagnetic metal. But in any case, the lack of superconductivity in 327 is linked to the fact that this pairing mechanism has to be able to explain why the bilayer as well as it cannot get this superconductivity. In addition to that, as we heard from Stephen in the first talk of the series, that this in fact has a spin density wave when the field is applied. So here's the phase diagram of the spin density wave of 327 as we applied field along the z-axis. Here is just a window from a 7.5 to 8.5. We do see a little bound here of the spin density wave. This was, in fact, was suggested in quite a while ago by this St. Andrews group theorist in 2009, but this was very popular back then. This could be an electronic nematic state. So it was kind of not much of attention was made until Stephen has found that indeed there is a finite ordering wave vector and observed by neutron scattering. So that was this 2015. And since then, there has been a lot of studies on this high temperature and so on, which I won't have time to discuss. I'll focus on the zero temperature. So I just want to remind you again, the difference between the 214 and 327, there are two aspects. One is the bilayer and the other is a staggered rotation of octahedra. And I'll go one by one. Okay, so let me begin with so these are the puzzles that I'm going to address, and I'll probably jump to a conclusion first, and then I'll start with a bit of review or some basic ground. So here's my main research. In fact, that I am telling that this 214 is called the pseudo spin singlet, and the reason why it's a pseudo spin because the spin-orbit coupling is significant. And that is coming from inter-orbital spin triplet superconductors. So the pairing itself is actually a spin triplet. However, due to the spin-orbit coupling, this appears to be a singlet. And if we have 327 bilayer, I have generated this called 327 knot. And that means it's a bilayer without the staggered rotation. And this 327 is the one with the staggered rotation. So if I have a 214 and just to step one over the other and make the ideal bilayer, in fact, this particular interorbital spin triplet is not destroyed. It is in fact enhanced due to the bilayer, and the superconductivity here is going to be even bigger, stronger. And that means that as a functional field, here is the magnetic field along the z-axis. This superconductivity is going to stay even longer than the single layer 2 on 4. On the other hand, once we add back the staggered rotation, then what happens is that this superconductivity is completely gone, and this will be a paramagnet, low field paramagnet, and then there will be a spin density wave related to the some van 't Hoff singularity and nestings, and then high field paramagnet will appear afterwards. So that is what I'm going to present. So let's begin. So real scenario begins from here. So spin singlet, this is basically a review, and I was told by Peng Cheng that I should aim for a graduate student. So I prepared a few slides that will just remind you what are spin singlet versus spin triplet. So spin singlet is the spin 0 to particle total SC being 0, so it's up, down, minus, down, up. And that has to be anti-symmetric under the up and down here. Otherwise, summation over the K, this will go away. And because it's just anti-symmetric between up and down, coming from fermionic the nature, that this form factor F of the K, which we often call that pairing symmetry, like FK1 will be a S wave. FK having cos kx minus cos ky, we call that D wave. So this form factor FK has to be even under the Kn minus K. So we call that even parity. And often we write this as a theorist, instead of writing as up, down, minus, down, up, we introduce a Pauli matrix, which is the basis of up and down here, and rewrite them in terms of this Pauli matrix I sigma y. So whenever you see I sigma y, that means it's actually a spin singlet component, because you can write this 2 by 2 matrix and put it here 2 vectors, you will end up with this form here. So that is rather straightforward. Now, spin triplet is S equal 1. So we have 3 components, which will have S z equal 0, which is the first term here, up, down. Now it's a plus here. And down, up. And one can also have up, up, and down, down, which will be a S z equal 1 and S equal minus 1. The combination that I'm going to write is going to be up, up, minus here, down, down, or we can have up, up, plus, down, down, which is a plus here with I, the I imaginary here that look like identity in terms of Pauli matrix. So again, this has to be anti-symmetric, but now spins are up here. So instead of anti-symmetric under the spin, it is anti-symmetric under K and a minus K. So that is Fk has the minus F of minus K, and we call this as odd parity. Instead of writing this 3 component, it's very useful to introduce the vector, and that is called the D vector. So you see this D hat here. So this D hat represent each of this component. So when D hat is Z direction, then you can see that the D hat dot of sigma will take a sigma Z, and I sigma Y times the sigma Z will be a sigma X in total, and sigma X in this 2 component vector will give us up, down, plus, down, up. Now you can see that when D is along the X hat, then this X hat will be a sigma X here. Sigma Y, sigma X will give us a sigma Z, and therefore I end up with up, up, minus, down, down. You can see that this represents the sigma Z, and D equal to Y hat will give us, this is going to be identity operator, sigma Y times sigma Y, and then imaginary times identity. So instead of writing these 3 component vectors, each component, we often use this D vector to represent the different pairing state. Now, and then the notation is that because in this notation, I didn't include F of K, like odd parity, like sine Kx or sine Ky, things like that. If you include Fk together with the D hat here, and that is the D vector containing the momentum dependence. Okay, so this is what we use most often to represent the triplet superconductors. I hope that's clear. Now, so in the case of this, so this is example, like when D vector, D hat is along the Z hat directions, that means that pairs are condensed in the eigenstate of S equal 1, S z equal 0. So, and that means that you have up, down, plus, down, up, but that is in the quantization axis along the Z hat. So one way to think about that is instead, writing in terms of the x direction, for example, then you can think this as up, up, and down, down, condensed along the x directions. So that's called A phase, like helium-3. And consequence of those, one can detect by the experiment, because imagine that I apply the magnetic field along the in plane where this up, up, and down, downs are condensed. Then this up, up, and down, down will just simply rotate along the x direction. So when magnetic field is along the in-plane direction, then night shift will be the measure of the number of state that responds to the magnetic field will be same as the normal state. So the black line is a normal state light shift, the density of state. If I, in the superconductor across the TC, magnetic field along this in plane will be still the same. And that means that I only have up, up, and down, down pairs. On the other hand, if I apply the magnetic field along the perpendicular direction, I'm going to see the up, down, plus down, up, which was SC equals 0 component. So I have to break up and downs to respond to the magnetic field, so that the night shift will have this exponential decay, and that is same as the singlet. Okay, so d vector direction, you can imagine that magnetic field parallel to the d vector act like a singlet. Magnetic field perpendicular to the d vector will have a triplet and act like normal in this case in terms of spin response. Okay, so early development of this rutinate goes back to, again, as I said, it's a 1994. And right after this discovery has been a lot of work has been done. So, most importantly, there was a proposal that this will correspond to d vector here, z hat. So that's the d hat along the z direction. And momentum dependence here will go into the odd parity, sine kx plus I sine ky. And that's analog to the helium-3 A phase. And that's where the reason coming from is that the helium-3 A phase, the mechanism is coming from ferromagnetic fluctuations. And the one of 3D compound has a ferromagnetic metals. So that was where this proposal was probably originated from. And this was kind of well received because you can see the night shift here. This was done field in plane, and night shift had no change across the TC here. And that kind of confirmed that this might be a triplet with the A phase, where D vector is perpendicular to the magnetic field, which is the outer plane. At the same time, this was about around the same time, the MUSL has been reported that across the TC, the relaxation rate has increased. So that means there is additional magnetic field that is generated inside the superconductor, and that will give us a muon to relax faster. And that has proposed that probably time reversal symmetry is broken, so that near the defect, there'll be a kind of supercurrent which might generate the small magnetic field, and that give us relaxation to the muon. So in fact, that this was brought up a lot of attentions, as most of you know, but things becomes much more difficult because there are indications that this may not be a triplet even before 2019. And I refer to this Andy McKenzie's review articles. In fact, there are a few of them, and this is probably one of the most recent ones, and to go back to see what the early studies have been telling us. Okay, so recently, as you heard, that in fact this 214 night shift was done it again, and this is a UCLA Sr2RuO4 group, and has seen it that here is a night shift as a function of temperature again, and here's a TC, and this one was done under the strain. So you can see that they put some uniaxial strain. And once you put the uniaxial strain, TC grows a bit, and you can, and then under the, so you can see the epsilon AA here is equal to epsilon V, meaning that the strain in such a way that this system hit the Van Hoff singularity at this point, and that's where this measurement was done. And notice that the night shift actually does drops. So here's a TC and a night shift on a one of auction site, and this is a night shift in another auction site like O1 and O1 prime, and these are two different auction sites, and they do see the both case. The night shift has a reduction, and this was in fact reconfirmed by the Ishida's Matsuda's group again, and they also confirmed that indeed the night shift, when the field is along the a-axis in the plane, it does drops. And that means that it questions strongly that this is not a triplet superconductors, at least not a simple triplet ones. Okay, so that was the, just remind you that that's the development. And of course, there has been many others. I don't have time to go through all of them, so I just brought up the most relevant one for my talk. Okay, so now let's think about the reality of the system 214, 327. These are the D4, and we know the Fermi surface in the normal state, and this was done in earlier. You can see this 1996 in the background. This has this red spots, the Fermi surface. And we did it in early 2019s, and this one you can see even much better resolution. And this is going to be the Fermi surface with all T2Z band that are participating. So that's the multi-orbital that we have to take into account. And there are three bands, alpha, beta, gammas. And not only that, these multi-orbitals, but also the strong spin-orbit coupling is not small. So here is an ALPS data with the spin reserved. And you can see that the red refer to the downspins, blue refer to the upspins. And as you move along the momentum space, the low referring to the XZ and the YZ orbitals, things are in the plane like this is an XY orbitals. And XY orbitals here is upspins, and you can see that XZ orbitals are downspins. So spin-orbit coupling in particular mix when three band are nearby. And that makes sense because that breaks the degeneracy when the band meet each other. Okay, so as we discussed earlier, the superconductivity requires antisymmetric wave function. And that means that once we have a triplet, this D vector, which represent the those S equal 1 condensation, should have odd parity. Otherwise, they cannot be antisymmetric because up, changing up does not make any difference. So in a single band or a single orbitals, this requires odd parity. Examples like a P wave or sine kx or sine ky. But since we have a multi-orbital, we have multi-band. In fact, that another thing is allowed is the even parity triplet pairing is also allowed. In other words, I have additional degree of freedom, which is orbital now. Let's call AB, and we can make AB to be antisymmetric. So here's an example, and here is the A here and the B, and I make the AB, switch the B and A here, and then had a minus sign. So this is antisymmetric under the exchange of the AB orbital. On the other hand, my momentum K and minus K is still symmetric. Sigma is a sigma here, sigma, sigma. So there's no change in the spin. So it is symmetric under spin and momentum, but it is anti-symmetric under the orbital. So often this is called orbital singlet, spin triplet, or some people call just inter-orbital. And dk contains the K and minus K. So this is even parity spin triplet. So when you have a multi-orbital interactions, this is where things becomes rather complex, but it's a reality that we have to take into account is that we have not only Hubbard interaction for our same orbital, we have a Hubbard interaction between the two different orbital A and B here on on-site. This is on-site interaction, two different orbitals here. And we also have a Hund's coupling, which is exchange process between the two orbitals, which like to align each other. And that is the Hund's coupling. So in these situations, one can think about, okay, what are the instabilities of the Kanamori? This is called Kanamori interactions. One can decouple these interactions into some order parameters. And because I'm going to do just a simple mean field theory here, which is very intuitive. Of course, the number-wise, the quantifying the within a mean field, one has to be very careful. But in any case, I'm going to decouple them in the pairing channels, which are this orbital singlet, spin triplet, AB here, as well as it also allows to have a spin density wave, which is the magnetic ordering, M and M here. This one is intra-orbital because it's coming from the Hubbard interactions. So effective interactions, you can see that for the triplet channels here, is going to take effective interaction of U minus 3JH. In fact, it's U prime minus JH, and U prime is U minus 2JH. So that's where they're coming from. And as we know, Hubbard interaction like to have a spin density wave here, the magnetic ordering. So that is the attractive part of these interactions. So order parameter here, delta, as I wrote earlier, it's a spin triplet. And remember that if I had only sigma y here, it's a spin singlet. Now I got sigma L here. So L is going to represent X, Y, Z, and that is going to take the D vector direction. Okay. And AB minus BA, so it is orbital anti-symmetric, and that's a spin triplet. And spin density wave or magnetic magnetization here is going to take the normal standard C dagger C with the sigma, which is the spin sigma sigma prime, spin half Pauli matrix here. Okay, and interactions that we are going to take is the value of U is throughout this analysis, we are going to keep the interaction strengths to be the same for every three materials, 214, 327 without the staggered rotation, and 327 with the staggered rotation has all the same local interactions. And then the unit of the energy, I'm going to take this is 1 of XC, moving along the X direction, which is called pi bonding to be a 1. And that's the type of the ratio of the Hunds and the Hubbard interactions. And then I'll just discuss about beyond the mean field theory sometime later. Okay, so let me just illustrate what this means. So pairing is actually local in the given site I here. I have two orbital, A and B. And the Hund's coupling like to have them aligns parallel. And then J site, again, I have A, B, two orbitals, and then like to align in this way. Of course, this is local, but this system is a metal. So that means that we have a lot of hopping to coming in, and the system will form a band. So let's say that I have some sets of the hopping T, which can hop from A orbital to A orbital or B orbital B, or A and B can also mix because orbitals are not conserved. So this kinetic energy is going to form the band. Let's call alpha band and beta band. They are not A, B because A and B orbital can mix. Therefore, alpha Fermi surface will be a mixture of A and B orbital. Beta Fermi surface is another mixture of A, B orbitals. And if they want to make a pair, or if already they made a pair, kinetic energy is going to destroy them because you can see that this Fermi surface is generically not going to have the K and minus K at the same location, because the superconductivity in this case is still the Fermi surface instability. And if I want to pair the K and minus K, you can find that a lot of places we don't have such a pairing. So this type of the pairing is very fragile, and as it requires the degeneracy of the band. Like when alpha and beta band are exactly degenerate at every momentum point, then we can have pair of the K and a minus K, but that's not the case. And therefore, this type of the superconductor is very fragile. And this was noted quite early on. I think this is one of the probably first paper that was noticed about this orbital singlets. Now, in this ones, though, what has been missed is the effect of the spin-orbit coupling. So let's see what that does. Okay, so this was earlier work that we have done it. Then what we have noticed that this spin-orbit coupling is, first of all, if you look at this panel here, lambda is referring to the spin-orbit coupling, the atomic spin-orbit coupling at a given site. And when lambda is, it's a strength of spin-orbit coupling. When lambda is 0, the pairing, this is the dx dy, meaning it's a triplet pairing size along the x direction and y direction. And depending on what orbitals we have, the d vector is pointing different directions. For example, if I have xz and xy orbital, the d vector is along the x directions. Condensation can happen in a very different way then. And then this pairing will happen along the y. If I have x, z, y, z, it's the d vector is along the z axis. So it's not having a uniform d vector along one direction. In fact, the d vector moves in momentum space, depending on the mixtures of orbitals. And you can see that when lambda is 0, pairing occurs, requires quite a large attractive interaction. But as the lambda crank up from the blue, the black to a yellow, you can see that the pairing will appear, almost immediately as soon as this interaction become attractive. So spin-orbit coupling enhances the interorbital, even parity triplets, and not only that, it also pins the d vector directions. And the d vector directions varies in the momentum space because it depends on the orbital composition. Now, as I said, this is metal. So, and spin-orbit coupling here is smaller than the bandwidth. So we better to think about this in the band picture. And that's where the little difficulty comes in. But let's see if I can convince you how this look like. So as I said, the band degeneracy breaking terms will destroy this type of the superconductivity. And so to understand that, let's consider two orbitals. So let's have xz and yz orbital. These are T2z, so there's a dxy orbitals, but it's easy to understand having two orbitals first and then add another orbitals later on. Okay, so if I have xz and yz orbital, this is in the xy plane, scale lattice, and then c-axis is out of the screen here. And we will have a hopping at least the three different kinds. In the simplest case, T1 will be along this y-xc with along the x direction. YZ orbitals will go along y directions. So that would be T1 here and T1 there. By the symmetry, this T1 has to be the same. And T2 is going to be weaker because it's kind of delta type of the hopping. So this is T2 appears in the y direction for xz orbitals, while T2 appears for the yz orbitals along the x directions, which is here. In addition to that, there will be a TAB, which is the mixtures, like xz orbital can hop to yz orbital. So this will be an orbital mixing between the two orbitals, and that's where the orbital is no longer conserved. So there are two terms that are important. One is the difference between these two dispersants. I'll call that xi minus or orbital hopping difference. And you can see that that's coming from the fact that T1 is different from T2, and that is T1 minus T2. And it has this interesting cos kx minus cos ky form factor. And another one is this TAB here. That is the orbital hybridizations. So TAB here will generate the 4 times TAB sine kx sine ky. So this is just taking into account nearest neighbors and second nearest neighbor. One can add third nearest neighbor, fourth nearest neighbor. It really doesn't matter, as even though they get smaller. These are the terms that will break the band degeneracies, these two, both of them. So let's begin with some picture. So I'm going to add the superconductors, starting from some superconductor, and see how this effect are going to affect the superconductivity. So here is my black line in the middle here. I artificially make the xz, yz orbital to be degenerate, okay? Which is, of course, in reality, it's very difficult because T1 and T2 are not going to be degenerate because are not going to be same because I mean, their orbital shapes are very, very different. But let's say that I start with the degenerate band here. So here is a xz, yz orbitals that degenerate, and I slowly turn on the orbital hybridizations, which was the xz and yz hopping. And as I turn on, what I notice is that what we notice that this delta divided delta max, and you see that the colors as well. This one is all, everything is sign, same sign, positive, because I start with just a simple the atomic spin-orbit coupling. And you can see that when TAB grows, the degeneracy of the band is going to split except this point, because sine kx, sine ky along this point is basically 0. So here TAB is going to grow, and notice that this color is going to diminish. So that means that this orbital hybridization is going to destroy this type of interorbital superconductivity. And same for a T minus, which was orbital hopping difference, T1 minus T2. Now you start to see a more realistic band here. So I starting from this band here, which was having a TAB, which is the last stage of this band here. And now turn on the T minus, hopping difference between XZ and YZ. And you can see that they almost have destroyed the completely superconductivity is gone. So that is consistent with what has been observed earlier, that once this band no longer degenerate, in fact, that this interorbital superconductivity cannot survive. Now, on the other hand, there's another way to break the degeneracy, which is a spin-orbit coupling. So here I start with both the orbital hybridization and orbital difference was added. So this is the last band that we had. And now turn on the spin-orbit coupling. And now you start to see that the spin-orbit coupling lambda naught is going to increase. And what happened here is that, in fact, the superconductivity will increase again. It's growing back, despite the degeneracy is even further broken. The band are getting further away in energy, but the superconducting intensity is growing up. So, and notice that there is a color change. So in fact, that this is going to take a plus sign and this is going to take a minus sign. So it's not a simple S-wave pairing. It is actually appears to have S plus minus pairing. And if I had a spin-orbit coupling, which has a cosine kx minus cosine ky, it's going to take the form of this spin-orbit coupling. See that the blue is here, pairing sign, the changes from blue to red, and then red to the blue. As you increase, again, the pairing intensity grows. And this can be seen from some mathematical notation here. So here is the punchline. In fact, that we begins from triplet superconductor with a d vector in the xyz orbital. D vector is along the z direction. That's a d hat. And this one will combine with the spin-orbit coupling lambda. Lambda can take the momentum dependence or can take just no momentum dependence, like lambda naught here, depending on the lambda form of the lambda here. In fact, we convert this triplet into a pseudo-spin singlet because this appears in the intra-band. So appears to be in the same band, which always will have the k and minus k pairs. And that's why spin-orbit coupling enhance the superconductivity and also determines the pairing symmetry, because this momentum dependent lambda k will carry it over to the intra-band pseudo-spin singlet. Okay, so in fact, this is not as simple as what I said. If I go in even a two-band model, it's not only having a one component. In fact, we have pseudo-spin singlet intra-band with the minus sign here referring to S plus minus. In addition to that, there are pseudo-spin triplet up here. So it is in fact a multi-component superconductor. However, pseudo-spin singlet, because they appears in the intra-band, they are the dominant terms. Like their strength is the largest, and we can often forget about this interband singlet here, interband triplets here. Okay, so these are just the formula that I wanted to just want to show you again. Okay, now I just want to say that this can be compared with you may have heard about this Majorana formula, P plus IP superconductors, where people have a simple S-wave superconductor attached to a strong Rashba spin-orbit coupling. Then Rashba spin-orbit coupling actually breaks the inversion symmetry that allow to have odd parity combined with S-wave superconductor effectively on that surface or on that particular interface between the S-wave superconductor attached to the strong Rashba spin-orbit coupling material. In the band, they effectively act like a P plus IP superconductor. So is not very different from these pictures, except that we don't break inversion. So we never get anything like changing of parity. Our parity is going to stay as we studied because we don't break the inversion symmetry in this case. Okay, so this is a summary for the superconducting state. As I said, there are two different ways to break the degeneracy of the band. When the band that degenerate, the inter-orbital superconductor is going to be stabilized, but due to the kinetic energy that breaks the degeneracy between those orbitals, and band will appear and that will destroy the interorbital superconductor. And that is this TAB, T minus here. But on the other hand, another type of band degeneracy breaking term, which is the spin-orbit coupling, that will enhance the pairing, as I said, and not only enhance the pairing, it also determines the pairing symmetry. So at the end of the day, this is going to be a battle between non-spin-orbit coupled degeneracy breaking terms, such as orbital hybridization and orbital dispersion difference versus spin-orbit coupling together with the Hund's coupling. So if I had a strong Hund's coupling and significant spin-orbit coupling, in principle, we can stabilize inter-orbital even parity spin triplet, which will appear as the intra-band pseudo spin singlet. Okay, good. So that was the mean field theory, and I just want to have just two orbitals because going beyond is rather too complicated. The physics stays the same, except that the d vector directions is going to change as you change the momentum space because the orbitals mixtures are going to change. Now, beyond the mean field theory was done by these people in Sherbrooke, and they have found that the Hund's coupling is not necessarily has to be that big. They do see that as a function of Hund's divided by Hubbard interaction here, that there is a window where the even parity triplet superconductor, in fact, does appears when the Hund's coupling is about 10% of the Hubbard interactions. So remember in the mean field theory, we had to do the JH artificially large, but if you go in an effective low energy theory, most likely we don't need to have such a unrealistic Hund's coupling. Even with a realistic Hund's coupling here, such a type of interorbital can be found. All right, so now let's see the bilayer 3 to 7. So I just want to check the time, make sure not. Okay,
you still have time. Yeah.
Okay, good. Yeah, so let's now move to the bilayer. And I told you that the puzzles are why then the bilayer miss the superconductivity, because if you're starting with the local interaction, which is not much necessarily related to the structure, but of course that remember this difference between the two will in fact changes the kinetic part. So the bilayer and staggered rotation of octahedra is the one that are responsible for the absence of superconductivity in the bilayer case. So to work on this, we have to go one by one. So let's just think about the bilayer first, and then I'll talk about the staggered rotation of octahedra after. So we'll add the effect one by one. Again, this tilting is rather small, but that significantly changed the physics. All right, so this is just to conclude that just to show you what we have found, that in fact, the bilayer effect without the staggered rotation of the octahedra, we actually find that the superconductivity is not killed. It is in fact even bigger. Both of these are, by the way, 20 times modified because we have to put the spin density wave together. These are tiny superconductor, by the way, but this one is 4 times bigger than the single layer. So we were thinking like, okay, why that happens? And we said, okay, we better to look at how the orbitals and spins are mixed, because when orbital and spins are mixed through the spin-orbit coupling, that's the reason why the superconductivity can be enhanced, like work together with the Hund's coupling. And our Hund's is completely fixed in different series of material here. Then we could have better superconductors. So we look at the how this mixing occurs. This is the intensity of the spin-orbit coupling, like LX-SX or LY-SY. By the symmetry, these are identical, so we can just plot one side. And this is a quadrant of the Brillouin zone from 0 to the pi here. So in the 2-on-4 case, this spin-orbit coupling is most mixed along the diagonal direction, which makes sense because these are where the orbitals are most meet together. Therefore, this is where responsible for the pairing to occur. On the other hand, if I had a 3 to 7 without the rotation, this is just having a bilayer. So in other words, each of these alpha band bring into the 2 pieces, gamma band become a 2 pieces, and beta band become a 2 pieces. And we look at the spin-orbit coupling mixing here, and we do find that in fact this mixing is even higher in this bilayer. So here we have red curve here, and there is a red here, and this is why the superconductivity or pairing is even enhanced in the case of bilayer without the rotated staggered rotation or without the doubling the unit cell. Okay, so that's the one conclusion. And then we said, okay, now what happens if we add a staggered rotation of octahedra? And we found that once we add the staggered rotations, then the Fermi surfaces actually changes quite a bit. And there was no pairing occurs in the 3 to 7. So there's a completely paramagnet and no superconductivity, no magnetization. So these are self-consistent mean fields. So we also look at the SDW together, and SDW doesn't appear. So it is just a completely paramagnet as a function of the field. So again, we look at, okay, what about this mixing of the orbital and the spin through the spin-orbit coupling? And that again explains why there is a lack of superconductor in the 3 to 7 once we have the staggered rotation. The Fermi surface has to be not only bilayers, but has to be doubled because of the doubling of the unit cell. And you start to note that this red curve or red colors of the orbital and spin mixings are completely gone. And that's why this real bilayer 3 to 7 does not contain any superconductivity or any pairing. Okay, so that is actually quite contrast to the intra-orbital superconductor. So we also have calculated what happens if I have an intra-orbital pairing mechanism. Like we just added, okay, here is the intra-orbital pairing. You see sigma y here, that's the singlet case. So intra-orbital singlet with the xz and xy, xz orbital, which is same as yz by the symmetry, by the way. And then this is xy orbital singlet superconductor. In that case, you can see that 2-on-4, 3 to 7 not without the rotation. With rotation, superconductivity pairing actually increases as we make the single layer to bilayer and then bilayer with the rotation. So this is very different from the inter-orbital. And then we were thinking, okay, why this is the case in the intra-orbital case? And that goes back to the Van Hoff singularities. So this is noted quite a while ago that if you look at the Fermi surface of single layer, we know that there is this gamma has this this part here in the x near the x point here. There is this flat band here which give you the net, which give you a saddle point, and that saddle point to generate this Van Hoff singularities, which called coming from the gamma pockets, gamma near the gamma, near the x point from the gamma band. If we had a bilayer, this one also, the gamma actually split into 2, gamma 1 and gamma 2, and they still appears to be exist once we in fact make the staggered rotation. And these Van Hoff singularities are there, and since I have a lot of density of state, if I just have an intra-orbital superconductors like this one, this is going to be sensitive to the many density of state. So I have more density of state, and therefore all of these cases, the pairing will enhance. On the other hand, inter-orbitals are not just sensitive to the Van Hoff singularities. It is actually more sensitive to the nature of the underlying orbital and spin. So it's better to have more mixtures of orbital and spin through the spin-orbit coupling. So that's where the difference comes from. Now, the Van Hoff singularities plays an important role here, not for the interorbital superconductor, but for the field-induced spin density wave. So now, bilayer under the field, remember that it has the Van Hoff singularities in here, and they are very close to the Fermi surface, which are related to these little gamma pockets here. And that is this gamma pockets here. And this is where B is 0. And now what happened is that as we apply the magnetic field along the z-axis, so here's a BZ finite, and this part here, there was no Fermi surface. It will start to appear the Fermi surface, and that has this little flower shapes. It's cut off because we just plot the quarters here because it's too big, otherwise it's too complex. And now, because of that, there is a Van Hoff singularities appearing in this two sides. In addition to that, there's a nice nestings appears in this along this line here. And because of that, this two effect of Van Hoff singularity and nesting, which appears as a function of field, and that in fact generate the spin density wave. And the spin density wave has the direction, which is along the x, and momentum. The ordering wave vector is along the x direction, and the momentum here is going to take y component, and that has to be fixed because of spin-orbit coupling. So they are not like random. Once the ordering wave vector is along the y direction, the momentum spin density wave will take x component, in addition to Z component, which comes up because of the magnetic field. And they are bounded by these meta-magnetic transitions. And this part is actually quite sensitive to the tight binding parameters because this appears to comes through the nesting and the Van Hoff singularities. But no matter what one uses, we'll always have this window of the spin density wave, and that can be larger or smaller depending on the details of the tight binding models. So here's my main result again. As I said, we think that this superconductor has something to do with the interorbital spin triplets. Even though we call the singlet, they are multi-component through the spin-orbit coupling, but the dominant one is the pseudo spin singlet. And there's this spin density wave appears in under the field in the 3 to 7. In the ideal case, in fact, the superconductivity can be even have a higher TC if one can make the bilayer without the staggered rotation. So I think my time's up. I'll just leave my summary here, and we'll have take questions if any. And thank you for your attention.
Yeah, thank you very much. Yeah, so this is very, very, very interesting. Before I can see this hand, let me ask you a question. So then you're basically saying that if you include additional degree of freedom, such as orbital, then the pairing in the case of 214 is still spin singlet, right? And then basically the same as minus plus because you have this one additional degrees of freedom. So my question then is that wouldn't you expect that the electron hole Parker excitation between the plus and minus side to give rise to the enhancement of stability in the superconducting state at the wave vector, between the the split band due to spin overcoupling?
Right. That one I will be a little careful because yes, you're right. If I was just thinking about the single band with a plus minus, you will have a spin resonance connecting from the plus minus, just like a D wave.
Right.
Where the neutron comes in and coupled to just directly to a spin there. But here is the spin and there is orbital moment. So orbital moment is mixed with a spin. So what one has to do is that you comes with a neutron and neutron has to couple through the spin and orbital, not the pseudo spin. And that will probably change your form factor. So that means that your coherence factors is no longer going to be 1 minus delta, minus xi divided by EE, where we know that from a constant when you have the right plus minus. And that may not occur in this case. So one has to do the calculation with all T3.
I see. But do you actually understand there's a lot of neutron scattering data, by the European group, Marcus Brandon's group. Do you actually understand, the fact that they observe both, the income entry is very well understood, right, in terms of Fermi surface nesting. But how do you understand the ferromagnetic part they observe?
I'm not quite aware of that one.
Oh, okay, that's fine. Okay, but
I
you
know the
can,
incommensurate one for sure.
Okay, but it's amazing that you can actually, based on your Fermi surface nesting picture, predict, the spin density wave that's seen in 3.2.7 by Stephen. Actually, the question I have then on that is that, do you expect lattice distortion to occur as well in the spin density wave phase?
The lattice distortion.
Accompanying the spin density wave phase.
I don't think so, because in this case, at least the staggered rotation has already occurred, and that is that was leading to the nestings. So I don't see why they have to rotate even further. In other words, at least the structure transition is not going to occur. They'll be in the same space group. You can have more rotations, but that's not the different space group. You have a staggered rotation angle of 6-7 degree or 8 degree will be still in the same phase, same structure. So there'll be no phase transition in terms of structure.
I see. Yeah. So maybe Stephen, can correct me. So I don't remember quite right. I mean, so the lattice really does not change, right? In the case of spin density wave phase. I guess is Stephen still here?
Can you repeat the question?
Yeah. I mean, I was just curious whether when you see the spin density wave phase under the field, is there any evidence that the lattice changes as well? The field induced.
No, but there's no evidence, but that doesn't mean to say it doesn't happen.
I see, but I thought there was some ultrasound measurement also. I mean, I haven't, I'm not keeping up with literature in this field. Yeah.
There may be some ultrasound measurements. I don't know about them. Maybe Philip Gegenwart can comment on that.
Okay. Okay, Chandan, you have a question?
Yeah, I have a couple of short questions. The first is, given your pseudo spin singlet and real spin triplet, how do you understand the night shift? So is the night shift, is it measuring the pseudo spin or the spin, or I'm a little bit confused?
Yeah, night shift again is measuring of both. So in fact, that one has to, when we do the calculation, one has to take into account the both coupling to the spin and the orbital moment. And then one can see that, I'm trying to find my slide, sorry about that. One can see that it does drops in both cases.
Oh, it drops in both cases.
Yes, this is earlier ones, but we had done the calculation. Here we go. So this is the proposal. Yeah, this is it's some test that we like to do it, but you can actually see that. So these are the underlying D vectors. Of course, it's a pseudo spin singlet, but you can see this is not a function of temperature. We are always in the zero temperature, and we are looking at it as a function of the how far from the Van Hoff singularity. So you put the uniaxial strain to see the night shift drops, and these are normalized by the normal state, and you see a strong drops here. So, and that makes sense because pseudo spin, it's a pseudo spin singlet where the orbital as well as spins are blocked by the pairing.
Okay, thanks. And the second short question I have is, in your total interaction Hamiltonian, you set, if I remember correctly, you said U prime equals U minus 2JH.
Yeah.
What constrains U prime to this particular?
Yeah, that one is in the atomic limit because we are looking at the one site that is SO3 symmetry that you have to preserve.
SU3?
SO3? Yeah, SU2, SO3.
But does that hold even when you have spin-orbit coupling, or?
Okay, well, of course, that can feed back to it. Like if I had a spin-orbit coupling and then compute what is the U prime, then that will be broken. But at the moment, we are not feeding it back. So we are doing a kind of, just to put it as it is, like a high energy, high energy type. We just have it, and then we have a spin-orbit coupling. As you lower to the low energy physics, of course, they can affect each other, and then U prime can change. It doesn't have to be U minus 2JH. At the same time, spin-orbit coupling also can be normalized. So at a low energy physics, of course, those values can drastically change.
Okay, thank you.
It's not in this mean field scenario, but you can see that in this dynamical mean field theory, This is the DMFT calculations with the LDA. You can see that appears in this, which is much of low energy physics.
Okay, thank you.
Yeah, Stephen?
Could you say a bit more about the orbital susceptibility that you have there? It looks like you're saying that there should be a residual susceptibility. And is that like the same as the Van Vliet susceptibility that you would have in a transition metal, or is that something different?
Orbital susceptibility. What do you mean residual orbital susceptibility?
The graph that you just showed, I think in your calculation, the way you saw how the susceptibility drop with temperature.
Susceptibility drop with a function.
When you were answering the question about the night shift, I think you showed a graph with
right.
Oh yeah, that one is not a function of temperature. It is a
okay.
function of the uniaxial strain. Yeah, I don't know where it is anymore, but not this one. Yeah, this one, right?
Yeah, this one.
This one is as a function of delta.
Oh, okay, I see. So when you have this, the spin orbit and the orbital susceptibility that you mentioned, at zero temperature, would the susceptibility go to zero still, or would there be a residual susceptibility?
At zero temperature, so that will depends on the gap, like which I didn't talk about, the pairing symmetry. So if the, which is another big question. So imagine that I have a gap. So if I had just the atomic spin-orbit coupling, in fact, that I will have very anisotropic quasi-particle gap. And in that case, I will not have any residual susceptibility.
Okay. And can I ask a question about the 327? So, so you predict one peak there that looks like the A phase. Do you have an idea what the other, the second phase might be?
Yeah, so that's another. In fact, that the superconductor that we've done is not sensitive to much of the tight binding parameter we use. So all this, they are like we did a VASP, the LDA calculation to get the tight binding parameters, and you can have a small changes. So we'll still end up with inter-orbital superconductors. Of course, pairing symmetry will be very sensitive to what type of the spin-orbit coupling we have, because you can have a lambda naught, or you can have D-wave spin-orbit coupling, and so on. This part here, spin density wave, is not the case. We found that if we change the tight binding parameters slightly, we do have a little bump here, which I don't know if that is a different phase at this point. And this window of the STW can also change. And I think that's because of the fact that this are sensitive to this area near the gamma X point. So I don't have an answer for this B phase at this point. We haven't seen it, but in principle, one may be able to find if you look for hard. But we don't want to do too much, too much tuning to a parameter at this point. We were kind of happy to have this.
It's already not easy, right? To just actually understand the first, spin density wave phase.
Yeah.
Okay.
And I believe this direction is the same as experiment, isn't it? Like a QX and the momentum is Y, and you see this different component. So all of this has a different size because different orbital contribute to different magnitude of the spin density wave.
What are the different? But the picture you have there, it looks like there's just components along the Y direction.
Yes.
Yeah. So
That is the spontaneous ones. So spontaneous STW will have a y component, while the ordering wave vector will be x direction. These three are the magnitude of the spin density wave in a different orbitals. In the experiment, you are going to see all of it together. I don't think there is a way to differentiate them. They're all mixed actually when you are doing a measurement. Can you?
I see. Well, okay, I see they're all along y. Okay, I see the y at the bottom now. Yeah.
Yeah.
Okay, good, very good. I have some more questions, but maybe I can send you them or later because I don't want to take up everybody's time.
Okay, Philip.
Hello. Firstly, thank you for the very nice talk. I very much
nice
enjoyed
talk.
this. I have a comment and a question. I just wanted to maybe return to Stephen's question. I do think that you would have a Van Vleck susceptibility coming from inter-orbital effects, and I suspect or interband effects rather, and I suspect the night shift drop is due only to the intraband contribution to the susceptibility. But so that was the comment. I guess my question is, if for this local pairing, does this make it more or less maybe robust against local inhomogeneity in the superconductor, such as impurities? Strontium ruthenate is famous for its sensitivity to impurities, right?
Yeah, I think so. So at least that the starting point of the pairing is local. So if there is a missing ruthenium site or some impurities defect or something, yes, I think it'll be very sensitive. We haven't looked at it, but it's a very good question. Yeah, but I would think naively expect that it will be sensitive to the impurity.
Okay, excellent. Thank you.
Okay, I mean, are there more questions for Hae Young? Okay, if not, let's thank Hae Young again.
Thank you.
Yeah, thank you. Yeah, so Stephen, I'll send you a link for our separate chat. Okay, yeah.
Okay.
Yeah, thank you. Yeah, thank you, Hae Young. I'll see you tomorrow.
Bye. Yeah. See you. Bye-bye.
Yeah, bye.
Bye. Thank you.
Bye.